We now turn to the question of quantifying just how good our poll really is. So recall, this is our basic question. We start with a random sample of Bernoulli trials from an underlying population whose bias is P. We form the accumulated sum S sub n and look at the relative frequency of successes, S sub n divided by n. And the question is, how good is this really as an approximation for P? Now, the listener will well understand that we are dealing with a chance-governed process. And in a chance-governed process, errors are going to be endemic. We are not going to be able to, in general, get exact answers. We're going to have to provide approximate answers, and there's going to be a certain margin for error, an error tolerance that we have to suppose. In addition, the fact that this is a chance game means that repeated performances of this experiment will give, in general, different answers. And therefore, we cannot give absolute certainty that something is going to happen. We can only provide a probabilistic guarantee. In other words, if we say that there's a certain amount of error, we can have no more than a certain amount of confidence in our pronouncement. And this is because of the very nature of chance. And tying all of this together are the underlying data themselves. Our pronouncements are only going to be as good as the data, and in particular, the amount of data. So let us suppose now that the data have proper provenances. They, in fact, arise as a random sample. Implicit here is that there is independence in the trials and that an underlying population is being fairly and uniformly sampled. Once this is the case, then our performance guarantees are tied entirely with the amount of data that we have, that sample size n. The error, the confidence, and the sample size are three parameters, and they are intricately connected in this process. They form a dance where one influences the other. Of course, we now have ample reason to believe that this kind of empirical estimate of the underlying proportion P is good. We have good reasons to believe that this kind of estimate is principled. It is likely to give us good results. But we want more. We want a quantitative prescription as to exactly how good this is. Now, the listener should gird up her notational loins, because at this point we're going to have to inevitably delve into some abstraction. We're going to need notation, and we're going to have to understand how the notation fits into the problem domain. Right? So let's build this up by first starting to look at a simple, concrete example. So let us consider a setting where we are sampling from an underlying population, where a proportion P of 60% of the population is of a certain type, say 1, and the remaining proportion Q of 40% is of type 0. Let us say we sample randomly from this population. In other words, we have a random sample, and let's say we look at a sample of size 10. So here's an example. X1 through X10 are the results of Bernoulli trials, whose success probability is 0.6. But bear in mind, we don't know 0.6. This is something that we would dearly love to know, right? But we don't know it. It's a fixed number. It is going to be revealed to us gradually through the sample. So I generated a particular sequence using a random number generator on my computer, setting the bias to be 0.6, and here's the particular sequence I came up with. A 1, 2 zeros, 3 ones, and 4 zeros. The number of accumulated successes in our notation S with a subscript 10, in this case, is clearly 4. There are 4 ones in this process. And of course, we know, that the number of accumulated successes when there are 10 trials with success probability 0.6 is governed by a binomial distribution with exactly these parameters. 10 trials, success probability 0.6. The specific form of the distribution is known to us, right? And in our complex notation, we introduce the letter b for the binomial, and parameters 10 for the number of trials, 0.6 for the success probability, and the actual number of successes k runs between 0 and a maximum of 10 there. And these are given by the binomial probabilities, and you've seen by now what looks like a very familiar curve. In our experiment, we've got exactly 4 successes, and we've highlighted that in the figure, and this occurs for the case of 10 trials with a probability very slightly in excess of about 10%. Okay, now we are going to use S10 divided by 10 as an estimate of p, which is 0.6. In our example, S10 over 10 is 4 divided by 10, or 0.4. Our estimate makes a 20% error. The error is 0.2. And this leads to a more general question. Let's again keep the parameters p equal to 0.6 fixed. This is fixed, but a priori unknown to us. Let's fix the number of trials at n equal to 10. And let's say, the amount of error that we are willing to tolerate as, let us say, 10%. So, of course, in our example, we are making an error larger than what we can tolerate. We are making a 20% error for this data. But here now is a general question. If many people perform this experiment, in other words, a large number of people, each of them generate 10 trials according to this Bernoulli probability, what is the expected number of these individuals whose estimate of p, S10 over 10, differs from p by no more than 10%? Formally, what is the probability that the relative frequency of successes, S10 over 10, differs from the true probability, p equal to 0.6, by at most 10%? Well, let's promptly set this up. Right? Now, at this point, we're going to actually have to do a computation. Right? The basic question says, I want my relative frequency of successes, S10 over 10, to differ from p by no more than 10%. In other words, I want S10 over 10 to be no smaller than 0.6 minus 0.1 and no larger than 0.6 plus 0.1. And so, writing it out mathematically, we're looking at the probability that the relative frequency of successes lies between 0.5 on the one hand and 0.7 on the other. Now, we should promptly now figure out what the event at hand is. Let's clear the denominator by multiplying throughout by 10 and rewrite this as saying this is the probability that the accumulated number of successes in 10 trials of tossing a coin with success probability 0.6 is between 5 and 7. In other words, the accumulated number of successes is 5 or 6 or 7. And of course, in your figure, these correspond to 3 settings and with 3 particular binomial probabilities. Our event then is comprised of the 3 integers 5, 6, and 7, and by additivity, the probability of the event is just the sum of the 3 binomial probabilities. Of course, the notation is looking cumbrous and difficult, but bear in mind here that the number of trials n equal to 10 is fixed. The success probability, p equal to 0.6, is also fixed. And what's varying here is the number of successes, 5, 6, and 7. And all that is done is to write this expression down, and now all is over, bother shouting. All we've got to do is plug in these binomial probabilities into our expression for the binomial and simply add them. Here's a simple numerical estimate remaining. You could plug this into a local scientific calculator, plug it into your computer if you have a little software program, or you can simply fire up your favorite internet browser and in the search domain type in binomial calculator, and you'll find a variety of free binomial calculators are available for you on the internet. Plug in the parameters and you'll find these numbers. Add them up and you find that the desired probability is about 67%. There is about a 2 in 3 chance that your relative frequency of successes is within 10% of the true but unknown answer. We now have a principled estimate, do we not? Right. Now, two parameters that come into play here. The first, the amount we deviate from the true answer. This is the error, and the particular error tolerance we've specified here is 10% or 0.1. The second factor that arises here is the probability that we land within this error tolerance of the true answer. This is our confidence in our estimate. So we can roughly say that our estimate gives us no more than a 10% error with a confidence of about 67%. Now, this is a simple numerical example, and it's not very hard. But of course, we can't simply compute numerical examples again and again. It doesn't tell us very much about an underlying structure. We'd like to intuit, figure out what is the underlying analytical structure so we can make predictions from this. So we want to very quickly generalize this. Let's do this in two stages. First, let us keep the success probability, the proportion of the underlying population, fixed at 0.6. And now let us ask the following question. What happens as the sample size n increases? How does the confidence vary as I increase the sample size? Let's take stock and take a look at it again. So here's a basic problem. So now we have a sample size n, and we're looking at a relative frequency of successes in that sample, Sn divided by n. Of course, Sn now is governed by a binomial distribution corresponding to n trials of a coin with success probability 0.6, and of course we have these binomial probabilities which are now very familiar to us. We've already seen the case when n is equal to 10. In this case, the chance of making a 10% error is given by the sum of the three binomial probabilities for a number of successes equal to 5, 6, or 7. What if we increase the number of trials to, say, n equal to 50? Well, then we get a binomial distribution corresponding to 50 tosses of a coin with success probability 0.6. It is going to be centered at 0.6 times 50. In other words, it's going to be centered at 30. If the relative frequency of successes in the sample, S50 divided by 50, is to be within 10% of the true answer, then the relative frequency must lie between 0.5 and 0.7. 0.5 times 50 is 25, 0.7 times 50 is 35, and so this says the accumulated number of successes in 50 trials should be between 25 and 35, and now we simply add up the binomial probabilities. Bob's your uncle. It's as simple as that. Well, let's go one step further. What if we increase the number of trials to 100? Well, it's exactly the same game now. We now have a binomial distribution corresponding to 100 tosses of the coin. We want the relative frequency to be between 0.5 and 0.7. 0.5 times 100 is 50. 0.7 times 100 is 70, which means the accumulated number of successes has to be between 50 and 70, and we simply add up the binomial probabilities. Of course, doing this by hand is very soon going to become tedious. And of course, we'll want to have recourse to a scientific calculator or a program in the computer which calculates binomial probabilities, or just do it over the internet, type in binomial calculator, and just say, compute these probabilities for these parameters. And if you do this, you will find these numbers. The probability is about 67%, 2 in 3 when n is 10. It is about 89% when n is 50. It's about 97% when n is 100. Or let's look at it in obverse. The chance that your estimate will make more than a 10% error, your chance that your estimate will be above 0.7 or below 0.5 is about 1 in 3 when n is 10. It's only about 11% when n is 50, and it's a really small 3% when n is 100. It is clear that as n increases, the concentration phenomenon is working in our favor, and we are very quickly concentrating probabilities around the expected value. A relatively small sample is giving us very good estimates most of the time. Now let's quickly abstract the basic principles.